Just want to take a moment here to show you the backs of these antacid containers, and you can see the one here, Alka-Seltzer, and different brands do the same, do different chemicals, or the same brand can do several different chemicals. This one here is sodium bicarbonate, which is basically the same thing as Arm & Hammer baking soda. Calcium carbonate, it's the same thing that Lincoln Memorial is made out of. It's limestone. It's just ground up rocks. Same thing that makes stalactites and mites in caves. And then this one here is a combination of two different compounds, magnesium hydroxide, that's MgOH, and aluminum hydroxide, AlOH, parentheses 3 actually. This is definitely one I wouldn't use because aluminum is known to be related to Alzheimer's. Whether or not this one does or not, I don't know, but the best thing is to eat your food such that you do not have acid buildup in your stomach, and you don't need these weak bases here to try to neutralize your acid. Hello, chemistry. Here we are in section 2 of chapter 14, page 460. And we are talking about different kinds of acids and bases. We're going to talk about Bronsted-Lowry acid and base and a Lewis acid and a base. But before we dive into those, let's go back to section 1 just for a moment, and let's review what an Arrhenius acid is. Once again, I'm not going to ask you to know these names. I just want you to know what makes something an acid. So in this case, an Arrhenius acid is something that increases the hydrogen ion concentration, which really is the hydronium ion concentration. And the base is one that increases the OH concentration. So I don't care that you know that it's an Arrhenius, but I do care that you know that it's an acid. An acid is something that creates more hydronium ion concentration. A base is something that creates more hydroxide ion concentration. Now, Bronsted-Lowry. Again, I don't care about the name so much, but you need to understand that this type of an acid is an acid that donates a proton. Well, this is really what we've done already, so it may not seem very different, because any acid that's defined as an acid by Arrhenius is also a Bronsted-Lowry acid. So we went from a narrow definition with Arrhenius to a broader definition that includes everything that we had before. So you'll remember before we had this example of hydrochloric acid reacting with water, and it increased the hydronium ion concentration. By the Bronsted-Lowry definition, a substance that donates a proton. Well, did this hydrochloric acid give an H to the water? And the answer is yes, it lost it. So that makes this an acid. So we're going to see how something under a Bronsted-Lowry could be an acid, even though it does not increase the hydronium ion concentration. So here, same substance, hydrochloric acid, is reacted with ammonia. So the ammonia accepts the hydrogen and becomes ammonium, and we have the chloride ion without the hydrogen. So there's no hydronium here. So under the former definition, there's no acid base here. But under this new definition, there is an acid and actually a base here, because a Bronsted-Lowry base is a proton acceptor. So if we have a giver, there has to be a receiver. So the acid is the proton donor, and the base is the acceptor. So in this example right here, this is the acid because it gives the proton. This is the base because it accepts the proton. And we have some electron dot models here that you can look at, where you can see just the blue H there, and that blue H comes over to here. Notice none of the electrons have changed their locations. They're still in the same place. And this is why we say a proton. Why? Because yes, hydrogen is a hydrogen and electron, but it left the electron behind, and just the proton went over. So that's why we call it a proton donor. You can think of it as a hydrogen donor, but since the hydrogen doesn't bring its electron, we just call it a proton donor. Now, what's also interesting is here we have hydrogen chloride, which on the former definition was an acid, and here's water. Well, what was water before? We just called it water. We didn't call it anything else. But in this case, It's a proton acceptor. So if you're a proton acceptor, then who are you? You are a base. So here is where water can act as a base. Now, not everything has only one hydrogen that it can donate. Sometimes it could be more than one. So we actually distinguish the different types of acids by how many protons or hydrogens it can donate. Hydrochloric acid, again, can only donate one proton. So it is monoprotic. And that's pretty easy, mono meaning one. Now, if you can do more than one proton, then you are polyprotic. And we'll come back to this in a second. If you can do 2 exactly, then you are diprotic. If you can do 3 exactly, you are triprotic. Now, tri and diprotic are both polyprotic. Now, let's take a look at an example. Here's sulfuric acid. It can donate a proton to water. That makes water a base, and it turns into hydronium. And then we have this substance, which is hydrogen sulfate, and it can lose one more hydrogen. And so you can see this equation, this guy here comes down here and becomes, the product becomes the reactant, and it can give another one of its hydrogens to water and create another hydronium, and therefore the sulfate ion can be created. Now, you'll notice that this has one arrow. Whenever we're showing one arrow, that means it's a strong acid. It's pushing in this direction. Whenever we do 2 arrows, it means it's kind of weak and probably would prefer to be in this situation here. But it is capable of donating both of them. And then over here, phosphoric acid, which we like to put in soda and so forth. Notice that all 3 of them are sort of weak. And it can donate all 3 hydrogens. Notice that this product becomes this reactant, and so on, all the way down to where we get the phosphate ion. You should be able to do this on your homework, these equations, and your test. And they may not be identical, but the principles are still going to be the same. All right, one final definition for acids and bases, and this is probably the most difficult one. It's the least known and the least we'll talk about, but we still want to know what it is. A Lewis acid, and again, don't care about the name, but an acid in this case accepts electrons, which gets a little bit confusing because we talked about hydrogens accepting and donating and so forth. So a Lewis acid accepts an electron pair. So let's look at an example. So if we were to just have a hydrogen ion from somebody else, and it were to come to the ammonia, it could then come and accept those 2 electrons, those lone pair electrons that are on the nitrogen, and form ammonium. These are the same thing, and accept those 2 electrons. So if it can accept an electron pair, then it must be a acid. So let's take an example here of something that's not even got hydrogen in it. Silver. Silver could come over here and accept these 2 electrons, and it could be then a Lewis acid, and the ammonia could be a Lewis base because it is a proton donor, which is what we have over here. A Lewis base is a ion or molecule that can donate an electron. And by the way, you need to notice that it doesn't have to be just be a molecule. Like here we have an ion that is donating a hydrogen or a proton, and it is an acid, even though it's an ion. So you don't have to be neutral in order to be an acid. So here's a electron dot showing the Lewis acid is barium fluoride, and it does not have a lone pair. This is one that does not obey the octet rule, and it has the trigonal planar geometry, and it can satisfy the octet rule by accepting these 2 electrons here and forming this substance. And this guy here is the proton donor, so he's the base. This one here is the, I'm sorry, not proton, electron donor. The Lewis acid is the electron acceptor, and so that makes him the acid. So at the top of the page here is a summary of the 3 different types of acids and bases. Again, I don't care so much that you know the name, but I do want you to know the process. So if you see one of these processes happening, you can say, oh yeah, I can identify which is the acid and which is the base. And you don't need to know which type. And that concludes section 2.